Hello guys, welcome to the first of a series of videos on static equilibrium. The first thing we're looking at today is the classic hanging signs question. This question comes up in various guises quite commonly at A-level and almost all exam boards because it's a great way of putting linear forces, moments of inertia together and understanding of the basic idea of equilibrium, and that all forces are balanced in all directions. That's really what equilibrium means. So the question here is asking us to find the magnitude and the direction at the point that the beam is attached to the wall. So here's our beam, the black beam here. We have a sign which has a mass, and we have a K which has some tension in it as well. And we need to work out what is the magnitude and the direction of the beam at this point here. Now we can assume that this point here is a hinge to all intents and purposes, because one of the conditions of being in equilibrium is that there is no moment about any point on the system. And so we know that the weight of the beam acting down here, and the weight of the sign acting down through the centre of the sign, and the weight of the beam acting down through the centre of the beam, they're going to both create a clockwise moment about this point, and the tension will create an anti-clockwise moment. So if we take this to be a hinge, we can first of all work out the moments of the weight of the sign and the beam, and from that we can work out the tension in the cable. So let's get stuck into this. Let's take a look. I'm just going to make this so that I see all this permanently. If we assume the tension is acting in this direction, then we can take the tension and break it into two components. We know it's going to have a vertical component acting upwards, which is going to be given by T sine theta, or T sine 30 in this case. We also know there's going to be a horizontal component of tension, which is going to be acting this way, and that's going to be T cos 30. Now, at this point, we can say, we can put the weight of the sign in, we can say that's going to be acting there, and the actual weight of the beam is going to be acting there. Those two are both the same magnitude, so make those as roughly the same size. And straight away we can see, well, we've got an upward force from the tension and two downward forces, so they could potentially cancel each other out. But we've got a sideways force, we've got a horizontal force from the tension. At the moment there's nothing to counteract that. The only place we're going to get a reaction, the only place we're going to get a force that will counteract this sideways force to balance this out is from the wall here. So we know this is going to have some sort of reaction force, which is going to have to be that way. And I'm going to already make a very bold statement by saying that the reaction force, the horizontal RH, I'll call it, for the horizontal reaction force, is actually going to have to be equal to T cos 30, because there's nowhere else. I should get rid of that little red arrow because it's going to be green arrow because it's going to be in the way here. Because at the moment, you can see really this is the only place we can get a force to the right, and this is the only force to the left. And if they're the only two forces, left and right, and it's in equilibrium, they must cancel each other out. Now, if I draw that green arrow back in somewhere that's less in the way, the weight of the beam is acting down over here, the weight of the sign is acting down over here, we have a vertical component of the tension acting over there. It stands to reason, hopefully you can see this, that there must be some vertical, let's say a RV, a reaction vertically, which is going to allow these two weight forces here to create a scenario where there's no net moment at any point I, it's not rotating left or right. And so we should be able to see intrinsically that the direction, or the rough place the reaction force from the wall will be at some angle from vertical acting up through. It's worth mentioning very briefly at this moment, if the sign wasn't here at all, then the only force would be this vertical force here. And if there are only 3 forces acting, then all 3 forces must go through a common point. So we could actually extrapolate this line up to where it crosses the tension, and we would know for sure that this line would have to go through that. In this situation, because there are 2 forces, that's not the case. So we could find where the net force acts, but we're not going to do it that way. Now we're going to do it using moments. Anyway, let's look at this. So if we take this point here, and we just get rid of this for now, take this point here and say, well, this is going to be the pivot, the hinge, then we know we've got a situation where the clockwise and anti-clockwise forces, must be balanced. So the anti-clockwise moment is given by this one here. The length down here tells us, you can see at the bottom, we can tell this force is acting at 1 meter from the base. So the anti-clockwise moment, if I draw this over here like this, that means anti-clockwise, and this means clockwise. The anti-clockwise moment will be given by t sine theta, or sine 30, sorry, times by the distance. Now the distance from the pivot is, as you can see here, 1 meter. And that's going to be equal to the sum of the anti-clockwise moments. So if we think about the moment due to the weight of the beam, well, it's halfway because it's a uniform beam of 1 meter length. The force, the weight, the centre of mass will be acting through the centre of the beam, which is going to be ½ meter from the end. So the actual weight will be 10 times 9.81, that's going to be mass times by gravity, times by 0.5 meters. That is the effective position of the length of the beam. If we look at the weight, or the weight of the beam, sorry. If we look at the weight of the sign, or the centre of mass of the sign, well, you can see the sign's got a width of 0.2 meters. So we could say, well, it's going to be 0.1 meters from the end here, which means it's going to be 0.9 meters from this end here. So again, we'll put parentheses around these if we wanted to, but again, it's going to be 10 times 9.81 times 0.9 meters. Now, of course, with this, what we can do is we can simply shove all of this lot into our calculator and then divide it by sine 30 times by 1, and it will give us the value of the tension. And that's a fairly straightforward thing. And if you plug that into your calculator, which I've just done before shooting this, it comes to 274.6 newtons. So we won't worry about rounding and significant figures at this stage, enough to think about here as it is. So this means that, well, we know this now to be let's say 275, there we go, 275 newtons. Of course, now we can plug that into here. We can say, well, what is 275 times by sine 30? And of course, that's going to be half of that value. That's going to come to 137.5. Okay, newtons. And we can work out what t cos 30 is going to be, and we can say that's going to come to 237.8, 237.9, let's say 238 newtons, because again we can just take this value and times it by cos 30. So straight away we've got that, which means we also know what RH is, because earlier on we said, well, these are the 2 horizontal forces acting. So straight away I can put 238 onto there, and I know I now have the horizontal component of my reaction force at the base. Already we see the net is closing. Okay, so this means if we know the horizontal force, or the horizontal component of the force, then we know it's in equilibrium to the left and the right. But up and down, it's still not in equilibrium, and the reason for that is, what is the actual sum of these 2 these two weights. Okay, we know acting downwards, if we just pull this over to this side maybe, acting downwards all together on this beam, we have a force of, and I'll stick with red for this, well, we've got 2 because there's a beam and the sign, and the weight is 10 times by 9.81. That's the downwards forces. And the upward forces is, of course, well, it's T sine 30, which is 137, as we've just said over here, 137.5, plus whatever this vertical reaction force is. And so using this, we can say, well, in order to be in equilibrium, the total upward forces must balance the total downward forces, and so we can set up a fairly straightforward equation. We can say that RV must therefore equal RV plus 137.5 equals 2 times by 10 times 9.81. These are the downward forces, these are the upward forces, they must be equal to each other, and we can shove this into our calculator and we can work out what the vertical force is. And when we do that, it's going to come out to basically 59 newtons. Again, I'm rounding this for the sake of ease. It's going to come to 59 newtons. So there we go. Now we know 59 newtons. We know the horizontal component is 238. We know the vertical component is 59. We can therefore apply basic Pythagorean theorem to calculate the actual value of R. So if we take this down to here now, maybe make this over here, of course R is going to be equal to the square, you know, Pythagoras, a squared plus b squared and all that. It's going to be equal to the square root of 238 squared plus whatever it's going to be, 59 squared. Jobs are good, and that's going to give us a magnitude of 245. Boom. So straight away, there's our first part. Find the magnitude of the direct reaction at the wall. Let's find the direction. Well, the same applies here. Let's apply basic trigonometry. Let's say we're going to find that angle there. If we're going to find that angle there, we know that this length was 238. 238. We know that's the angle we're interested in there. This will be 59. It's going to be theta, so we're going to use tan there. We're going to say tan theta equals opposite over adjacent, 59 over 238. We get our calculator out. We do arctan of 559 over that, and theta will come out to around about 13.9, let's say 14 degrees. Okay, and so this is the simple method. Well, there's nothing simple about it. It's the method for working out the reaction force of a sign that's being supported by a tension in a cable. Okay, hopefully that helps you. You can see this as much as you will. Okie dokie, good luck.